Now, before coming to the Kerala scenario, just a background. In ancient India, astronomy and mathematics are seen to have grown in close connection with religion. And most of the inventions during that period were motivated from their daily requirements and religious needs. Consequently, the pace of progress was in accordance with the rate at which the user was refining himself. As a result of high intellectual activity, the twin sciences outgrew their original purpose of helping the religious needs and started to develop for their own sake in due course of time. Some of the important mathematical accomplishments are thus found embedded in religious texts like Vedas and other Vedic literature, Jaina canonical literature, etc. Vedic literature is a rich source of some of the important basic mathematical concepts that form the foundations for subsequent development of the discipline. Okay, I will not share that slide. Okay. Likewise, in Jaina canonical literature also, we get a lot of mathematical works. In the beginning, astrology, astronomy, and mathematics were tagged under Jyotisha and assigned a top place like the crest of peacock and the gems on the hooks of serpents. Now, today, mathematics is like an unseen string that holds all pearls and gems to produce a beautiful necklace. Mathematics provides all branches of science and technology to produce wonderful developments in this modern high-tech world. Now, in Vedic literature, we can see three important landmarks. One is the decimal system, the simple system of numeration in decimal scale that did not occur to the minds of mighty mathematicians such as Archimedes and Apollonius. The simple rule of proportion, rule of three, and later it is called the Trairashika, occurring in the Vedanga Jyotisha, that influenced the entire science of computations, and the theorem of diagonal of rectangle or base altitude hypotenuse theorem. Now we call it Pythagoras theorem, occurring in the Bodhayana Sutra that dominates entire geometry. Now these three form important landmarks on the vast tracks of mathematics. Now beginning with such simple and ingenious discoveries that paved way for the phenomenal growth of astronomy and mathematics, considerable progress was made during the subsequent periods, and India produced a galaxy of erudite scholars who contributed their invaluable share for the further development of the twin sciences. Among them, Aryabhatta I of 5th century AD could be said to have opened the doors of scientific astronomy and mathematics. With the two treatises, Aryabhatiya and Aryabhatta Siddhanta, which is not available. Aryabhatiya is available, Aryabhatta Siddhanta is not available. Aryabhatta launched a period of immense mathematical and astronomical activity with systematization. Now, in Aryabhatiya, Aryabhatta has given a separate section called the Ganita Pada for brief discussion of mathematical concepts and rules that are needed for a scientific study of astronomy. And this practice was followed by most of the later scholars. Consequently, the twin sciences, astronomy and mathematics, began to develop hand in hand, nourishing each other. Now, several important mathematical findings during that period are embedded in various astronomical treatises And in due course of time, several scholars began to write exclusive treatises on mathematics. Now, Aryabhatta was followed by Varahamihira, Bhaskara I, Bhaskara Brahmagupta, Lalla, Govindaswamin, Mahavira, Sridhara, Pateshwara, Aryabhatta II, Sripati, Bhaskara II, etc. And they have made substantial contributions in various fields such as Vyakta Ganita, arithmetic, Avyakta Ganita or Bija Ganita, that is algebra, Kshetra Ganita, geometry, Jyotpati is trigonometry, Varahamihira has contributed to trigonometry also. Now, after Bhaskara II, the main center of mathematical activity shifted to the Kerala region. Now, let us focus our attention to the Kerala region. Now, we can see that this narrow strip of land in the southwest corner of India had a long tradition in astronomy and mathematics, beginning with the legendary scholar Paraduchi of 4th century, who promulgated the famous Katapayadi system on decimal numeration that excelled the older Bhutasangya system of enumeration. Now, several scholars like Haridatta, Govindaswamin, Shankaranarayana, Udaya Divakara, Krishnacharya, Suryadeva Yajman, Jayadeva, Talakkulam Govinda Bhattatiri, and so on, have contributed their share for the development of the field sciences. However, with the emergence of Sangamagrāma Mādhava of 14th century, 1340 to 1425, there was a great upsurge in the mathematical and astronomical activities in this region. Mādhava hailed from the house named Bakulavishthida Viharam or Ilanji Ninna Palli. The first one is the Sanskrit name and the second is the Malayalam name. Now, it is in the village Sangamagrāma in central Kerala. This place is now identified as Alur, about 6.3 kilometers from Kallettunkara railway station near Iriñālakkuda in Thrissur district. And his house is identified as that by name Iriñāra Palli and Iriñāra Valli. Some of the important works by Mādhava that are available to us now are Venvaroha, Sputachandra, Madhyamanayana Pragara, Mahajyanayana Pragara, Lagna Pragarana, Aganita, Aganita Grahachara, Aganita Panchanga. Now, the mathematical work of Mādhava is not available to us now. Some of his startling discoveries in mathematics are borne to us through citations from the works of his disciples and successors. Some of the important findings by Mādhava are cited in the Aryabhatiya Bhashya and Tantra Sangraha of Nilakatta Somayaji, Yukti Deepika, Kriya Kalapa and Kriya Kramakari by Shankaravarya, Yukti Bhasha of Jeshtadeva, Karana Paddhati of Pudumane Somayaji, and Sadaratnamala of Shankaravarma. They all belong to the Mādhava school. Now, Mādhava was held in high esteem by his disciples and later scholars. Quite often they refer to Mādhava with an appellation, Golavid or Gola Tattvavid, meaning a master of theory of spherics. As pointed out by K.V. Sharma, probably the merit of Madhava's work entitled Golavada, a thesis on mathematics of spherics, might have had a great role in fetching this appellation, Golavid. Unfortunately, this Golavada is not available to us now. While the scholars prior to Mādhava made significant contributions to arithmetic, algebra, geometry, trigonometry, interpolation, and mensuration, etc., Mādhava studied circle and chords by breaking the barriers of finite using an innovative idea of infinitesimal and opened the so far unknown and unexplored passage to infinity, making startling discoveries in the field of infinite series and series approximations. Available contributions, mathematical contributions by Mādhava are so startling as to enable him a top place among the world mathematicians. So far, we don't have any information about Madhava's teacher or parents, but Mādhava was an excellent teacher and he groomed an industrious disciple and a great researcher, Kodasheri Parameshwara, who authored a number of astronomical and mathematical treatises of high standard. Parameshwara's son and disciple Damodara groomed another renowned versatile scholar Nilakanta Somayaji, who belonged to the period 1444 to 1545. Nilakanta was also a student of Parameshwara and has authored a number of important works such as Tantra Sangraha, Golasara, Aryabhatiya Bhashya, and so on. Shankara Varya of 16th century was another illustrious scholar belonging to Madhava school. He was a disciple of Nilakanta and Damodara, and another scholar, Chitrabhanu, and has authored elaborate commentaries like Kriyakarmakari, Vritti Deepika, and Kriyakalapa on Leelavati of Bhaskara as well as on Tantra Sangraha. Shankara throws a lot of light on contributions of various scholars like Mādhava, Govindaswamin, Sridhara, Jayadeva, Chitrabhanu, etc. Another important scholar belonging to this period, namely Jyeshtadeva, was also a student of Nilakanta and Damodara. His Yukti Bhasha in two parts is an excellent composition containing detailed rationale of mathematical and astronomical results. The first part is on mathematics and the second part is on astronomy, throwing light on important discoveries in the discipline. Mention may also be made of other great scholars of this period like Achyuta Pisharadi, Udumana Somayaji, Bharadwaja Disha, Shankara Varma, who wrote important treatises that contain a lot of contributions during that period. The period from the emergence of Mādhava up to 18th century may rightly be called the golden period or the glorious period in the history of mathematics in India because of vibrant mathematical activities and excellent mathematical contributions of high standard in the field of infinite series. The mathematical contributions during this glorious period lay hidden from outside world for generations, and hence this period after Bhaskara II was generally thought of as a period of relative inactivity in Indian mathematical history. But the treasure trove of highly advanced mathematical knowledge was brought out to light by some enthusiasts in the 19th century. In 1825, Lieutenant Colonel John Warren, in his Kala Sankalika, published a communication from George Heine, dated 17 August 1825, containing several infinite series on quadrature of a circle invented by the Hindus, collected from native astronomers. Later, C.M. Vish of Civil Services of Madras Establishment of East India Company spotlighted the torch of his investigation on selected portions of the four manuscripts, namely Tantrasangraha of Nilakanta Somayaji, Yuktibhasha of Jeshtadeva, Karanapaduri of Udumanu Somayaji, and Sadaratnamala of Shankaravarma, and revealed the treasure trove on infinite series before the Royal Asiatic Society of Great Britain at Ireland on 15 December 1832, and later published it in the Transactions of the Society in Volume 3, Part 3, 1834. Later scholars like Ramavarma Mari Tamburan, Akhilesh Iyer, C.T. Rajagopal and his team, and now present scholars, made further investigations in this area. Several modern mathematical discoveries are found to have been anticipated by Mādhava and his disciples in their own way. Regarding the mathematical contributions from Kerala, the historian Srinivasa Iyengar comments in his book, The History of Ancient Indian Mathematics, as follows. The development of mathematics came practically to a full stop, and scholars contented themselves with chewing the cud, studying the works of great mathematicians and producing here and there a small bright gem. This remark holds for the entire country except the state of Kerala in the southwest corner of India. Some mathematical work of this place, dating from 15th to 17th century, have recently come to light and contains mathematics of a standard which is startling and which sets a big puzzle to the historian. They are essentially astronomical treatises, but they give in accurate form what we now call degree series and Euler's series for pi, and a number of remarkable rational approximations and rapidly convergent series for pi. So this remark was made by Srinivasa Iyengar in this small book, History of Mathematics. Now, the Kerala mathematicians desired great accuracy in their astronomical computations. This motivated Kerala mathematicians and astronomers to break the barriers of finite and discover infinite series expressions for quadrature of a circle, trigonometric functions like sine, cosine, and square of sine. Detailed rationale and analysis of series is provided in the Yukti Bhasha of Jeshtadeva and Trigonometry of Shankaravarma. The peculiar relation between the circumference and diameter continue to attract the attention of Indian mathematicians from very early times. Their awareness about the incommensurability of circumference-diameter ratio and their eagerness to evaluate the circumference with as much accuracy as possible prompted them to formulate various methods to achieve their target. Now, commenting on the usage of the term asanna while giving the circumference of a circle with a given diameter, in the sense approximating or approaching. Nilakanta, in his Aryabhatiya Bhashya, a commentary on Aryabhatiya, observes, why is it that the real value is left out and approximating value stated? Let me say, it is impossible to state the actual value. Why? That unit which leaves no remainder when denominator is measured will leave a remainder if used again for measuring circumference. Likewise, the unit which leaves no remainder in measure of circumference will leave a remainder in the measure of diameter, right? Hence, if both diameter and circumference are measured by the same unit, the state of remainderlessness or no remainder, niravayavatvam, is never attained. Even if this is carried out further with utmost effort, only smallness of remainder can be attained, but not the state of no remainder. Using the concept of dividing the circumference using infinitesimally small units and using the concept of continuous and repeated summations, Mādhava obtained infinite series expressions for evaluating the circumference, sowing the seeds of advanced ideas of integral calculus and infinitesimal analysis. The nature of slow convergence of the series obtained prompted Mādhava and his team to make further study and analysis of the series, which resulted in the discovery of several rapidly convergent series and methods for series approximations and methods to accelerate the convergence of slowly convergent series. Mādhava successfully achieved his desired target in 3 stages. In the first stage, he derived an infinite series for the circumference C in terms of diameter D, using ingenious ideas and concepts of infinitesimals, limits, and continuous summations. The series discovered by Mādhava in modern terms can be expressed like this: C equal to 4D minus 4D by 3 plus 4D by 5 minus etc. Now, this series, being infinite in nature, for practical computation, we have to truncate it after considering a finite number of terms from the first and neglect the remaining tail of the series. So in practical computation, this truncation will cause an amount of error in the series sum. Hence, in the second stage, Mādhava introduces the concept of applying an end correction, Andhya Samskara, to the partial sum to compensate the loss of terms and thus try to address the truncation error problem. However, if a correction term is attached to the partial sum, the desired accuracy can be attained using lesser number of terms than without it. So without the correction term, we need a large, huge number of terms. With the end correction, we need smaller number of terms. Application of better correction factor further reduces the number of terms required to get the desired level of accuracy. So if the correction terms are refined, desired accuracy can be achieved with fewer number of terms. Better and better the correction terms, lesser and lesser will be the number of terms required in the partial sum. Hence, in the third stage, Mādhava proceeds to refine the correction terms successively using an inaccuracy minimization technique. Now, citing Mādhava profusely, Shankara and Jeshtadeva have given a detailed analysis of series and correction terms in the Kriyakarmatari and Yukti Bhasha. Now we'll have a quick look at the process. Now, first stage, infinite series C equal to 4D minus 4D by 3, etc., where C is the circumference and D is the diameter. This was derived in a geometrical platform by dividing the circumference into arc bits, etc. The second stage, the series is truncated. Take the partial sum. So the truncated series is n dash. I've taken n terms here. Now applying the end correction, that is minus 1 raised to n 4b into gn, end correction applied to the partial sum, that is Cn. Now Cn plus 1 minus Cn will give minus 1 raised to n 4b into this much. It is minus 1 raised to n 4b into En, where En equal to 1 by 2n plus 1 minus En plus 1 minus Gn. Now this term minus 1 raised to n 4b into En, that is called the Staulia, the inaccuracy factor, existing inaccuracy, Staulia, the existing inaccuracy or the error in the partial sum. Now this En is called the inaccuracy factor, Guna, call it Guna, inaccuracy factor. For ideal correction, this En must be 0. Now when En is 0, we must have Gn plus 1 equal to Gn equal to 1 by 2, half of 1 by 2n plus 1. But it cannot be taken like that. So a new correction, because Gn will not be equal to half into 1 by 2n plus 1. Gn and Gn plus 1 cannot be equal for small values of n. For infinite value of n, it is okay, but for finite value of n, it is not possible. So a new correction factor, Gn1, is obtained by adding the best fit term, a equal to minus 2, to the denominator of Gn, so that the Staulia becomes a minimum. Thus, Gn1 is equal to, now that a is minus 2. So Gn1 is obtained from this, that is 1 by 4n plus 2, by adding a to that. 1 by 4n plus 2 plus a. Now a is minus 2. So 1 by 2n plus 1, 2 into 2n plus 1, that is 1 by 4n plus 2 minus 2, that gives 1 by 4n. And the corresponding Staulia factor, that is error inaccuracy factor, is En1 equal to minus 1 by 2n plus 1 cube minus 2n plus 1. All these derivations are given in Bhasha as well as Kriya in their own words. We are putting it in the modern notation. Now in the third stage, the correction factor is refined further. That is, from Gn plus 1, the next refinement, that is Gn2 from Gn1, the first correction, Gn2 is derived by adding a best fit fraction of the denominator to itself. That is 1 by 4n plus Gn1. So to the denominator 4n, a fraction a by 4n is added, and the best fit value of a is obtained as 4 using the inaccuracy minimization algorithm of Mādhava. So, and the corresponding Staulia becomes minus 4 by this. Now the next approximation is also obtained, that is Gn3, that is obtained by adding a best fit fraction of the denominator to itself. So 1 by 4n plus 4 by 4n plus a by 4n. And the best fit value of a is found to be 16 using that algorithm. And the corresponding Staulia is like this. So proceeding like this. So they have given up to Gn3. So we can compute Gn4, Gn5, etc. like this, proceeding the same manner. The value of a comes out to be the first one 1, second is 4, that is 2 square, the next one is 4 square, that is 16, the next is 6 square. So 2, 4, 6, X will be 8, and so on. So we can compute the successive approximations to the end connection and calculate the corresponding minimum Saulian. So higher order correction factors can be obtained in the same manner. Now, just to compare it with the modern value, Thomas J. Osler of Rowan University has published an article in the Mathematical Gazette in 2009 March, which gives a correction term for the series, alternating series, sigma 1 to infinity minus 1 raised to n plus 1 fn. The correction term is given as a of a plus 1 equal to 7 f of a plus 1, that is the n plus a plus 1th term, plus f of a plus 2 of the term, minus 2 into f of a plus 3, that is a plus 3 of the term, by 12. And that is derived from Euler-Maclaurin summation formula. So this correction term is prescribed for an alternating series by Thomas J. Osler. Now his article shows the number of terms of Leibniz series with and without correction term a of n plus 1 to get an accuracy of 2, 5, 9, 11, and 14 decimal places. So a table is given in that paper. Now let us compare with the Mādhava series. Applying the same procedure for Mādhava series, that is c by d equal to 1 minus 1 by 3 plus 1 by 5, etc. The corresponding a of n plus 1 will be 64n square plus 27n plus 1 plus 26 divided by this. The following table is constructed to compare the efficiencies of the correction term a n plus 1 given by Thomas with each of the correction terms gn1, gn2, and gn3, and gn4 we have added. The others are given by Mādhava. gn1, 2, 3 are given by Mādhava. gn4 we have extended that. So we are comparing with Mādhava correction term and the Thomas correction term. Number of terms required to get an accuracy level of number of decimal places 2, 5, 9, 11, 14 without end correction and with end correction. The first column is Thomas J. Osler's correction term, and these are Mādhava terms. It is the first correction. This is the next refinement, the third refinement, and fourth refinement. Mādhava has given the first 3 refinements. The fourth we have added. Now we just compare and compute the value of the sum. By attaching these, we can see that to get an accuracy of 2 decimal places without end correction, you require 500. With n plus 1, you require 10. And using the fourth refinement of Mādhava, you get the accuracy in 2 terms. Using the third refinement, 2 terms are required. Using the second, 3 terms are required. Using the first one, 5 terms are required. Now it goes on like that. Now let us take the maximum, 14 decimal places. Without end correction, we require 5 into 10 raised to 14 terms. We are not attaching any end correction. We require 5 into 10 raised to 14 terms to get an accuracy of 14 decimal places. Now with a n plus 1, we require 1 lakh, 100,000. These 100,000 terms are needed. With the first approximation given by, our first refinement given by Mādhava, 50,000 terms are required. With the second refinement given by Mādhava, 660 terms are required. With the third, 116 terms are required. And with the extension of that, fourth, we require only 47 terms. So without that, you require 5 into 10 raised to 14, and with the fourth refinement, you require only 47 terms. With an plus 1, you require 1 lakh terms. So that shows the efficiency as well as the improvement occurring with the each refinement. The efficiency of Mādhava's correction terms increases with the successive refinement. All correction terms by Mādhava are very much superior over the correction terms derived by Thomas J. Osler from the Euler-Maclaurin summation problem. So that shows the merit of the contribution by Mādhava. Now, apart from rational approximations to series, introduction and refinement of remainder terms, correction factors, and evaluation of corresponding inaccuracy, some rapidly convergent series are extracted by Mādhava and his team from Staulya. That is the existing inaccuracy factor. Some of the series for circumference by Kerala scholars are shown here. The first one is slowly convergent. The second one is the first series attached with the end correction. The third one also with another refined end correction. Now the fourth one is derived from, now incidentally, from the error En, from the En, that is the Staulya factor, rapidly convergent series can be derived. From the En factor, that is Staulya factor of a slowly convergent series, we can derive rapidly convergent series. This is one of them. C equal to 16d by 1 raised to 5 plus 4 into 1, etc. That is rapidly convergent series, and that is derived from the Staulya factor. One of the Staulya factors. Now, another, all these are rapidly convergent series. Another set of series like this. Now, another set, all these occur in various works. Now this one, okay, the last but one occurs in Karana Paddhati of Pudumane Somayaji. The other series occur in most of the works. Now Mādhava series for trigonometric functions like sine, cosine, and square of sine. Instead of sine, instead of cosine, they were using Utkramajiya, that is r minus r cosine, r cos x, r minus r cos x. From that, we can get the series for cosine. Now, hello, can you hear?
Yes, we can hear you, sir.
Okay. Some disturbance, I think. Okay, Mādhava series for trigonometric functions, antidates Newton's power series for sines and cosines. Madhava's formula for not including all the results. It will take more time. Madhava's formula for expansion of trigonometric functions in the Taylor series form, antidates Taylor series approximation up to second order. Now, several methods for improving accuracy of tabular signs and different tabular sign difference of tabular signs. They are needed for interpolation of signs. So different methods are given for improving the accuracy of tabular signs. So Bolasara has given a beautiful method for construction of tabular signs, and that can be used for construction of tabular signs or 24 values or 48 values or 96 values, etc. Now, different interpolation formulae are given by Govindaswamy, Mādhava, Parameshwara, Nilakanta Somayaji, Shankaravadiya, Jeshtadeva, and all these are anticipations of Newton's forward interpolation formula, Newton's Stirling formula, Newton-Gauss formula, and so on. Of course, we have many of these formulae from Vateshwara Siddhanta, which is rich in interpolation. Not covering those works. Vateshwara is not from Kerala. I am concentrating only on the Kerala. Now, Parameshwara's third order formula, which occurs in Siddhanta Deepika, anticipates Grigory's expansion of third order Taylor series, approximation of sign. Now, all these interpolation formulae are used for interpolation of signs and not for other functions. But they can be, they are all applicable for other functions as well. Parameshwara's formula for inverse interpolation of sign occurring in Siddhanta Deepika is a forerunner of the mean value theorem of differential calculus. Parameshwara's formula for circumradius of a cyclic quadrilateral antedates Euler's formula, Genevian mathematician Euler of 18th century. Parameshwara belongs to 14th century. Parameshwara's interesting concept of three diagonals for a cyclic quadrilateral, namely Ishtakarna, any chosen diagonal, Idarakarna, the other diagonal. So these two diagonals we know already, Ishtakarna and Idarakarna. So Ishtakarna is chosen diagonal, Idarakarna is the other diagonal. Now he talks about a third diagonal, that is Bhavikarna, the forthcoming diagonal, given by, without a geometrical figure, it is difficult to explain that, but mathematically we can explain it easily. Algebraically we can explain it simply. So that is given by, these three diagonals are given by d1 equal to root of p2 p3 by p1, d2 equal to p1 p3 by p2, and d3 equal to root of p1 p2 by p3, where p equal to ad plus cd, p2 is ad plus bc, and p3 is ac plus bd, where a, b, c, d are the sides. Now algebraically we can explain the three diagonals. If a, b, c, d are the four sides of the cyclic quadrilateral, we can form AB plus CD, AD plus BC, AC plus BD. So these three, P1, P2, P3 are possible. Now with P1, P2 and P3, with P1 in the denominator, with the P2 in the denominator and P3 in the denominator, and the other two in the numerator, we can have these three possible values. So the first one is one diagonal, second is the other diagonal. Then there is a possibility of the third diagonal. So algebraically, we can explain it. But without a figure, it is difficult to explain what the third diagonal is. So he's giving an interesting concept of the third diagonal, three diagonals for a cyclic quadrilateral. Now, coming to the desiderator, what we need today, simply talking about the past glory is not enough. So we have to do something. The present generation has to do something. Now, K.V. Sharma, in his 1972 survey, has mentioned 402 Kerala works, 211 Karana texts, 34 Tantra texts, and 6 Siddhantas. Now, in 2002, he has conducted a bigger survey. So, K.V. Sharma's 2002 survey on Kerala and Tamil Nadu manuscripts mentions 3,473 science texts, 12,243 science manuscripts from 395 repositories in Kerala and Tamil Nadu, 936 on astronomy and mathematics, 450 in Sanskrit from Kerala during the golden period, 1350 and 1840. Now, exhaustive national survey. I don't know whether a national survey has been conducted, I don't know. I have come across a work like A.V. Sharma's survey on Kerala and Tamil Nadu. So, in the same pattern, an exhaustive national survey can be done to get a full picture of surviving, unrecognized, uncharted, unexplored literature in Sanskrit and regional languages. Now, preservation of these manuscripts in original form is very much essential, and it is being done, I suppose. It is being done using modern technology. Digital archiving can be done. Now, edition of the manuscripts, only a very small percentage of manuscripts have been edited so far. Others are still lying in the repositories. Now, translation into English or regional languages, only a very small percentage has been done so far. Now, from among the translated works, only a very small percentage have been studied and expounded in modern terms. Now, exploration of the contents of the remaining identified literature has to be done. Now, for the study, what is required is a sufficient knowledge of mathematics, working knowledge of the language and the script used in the manuscripts. In the past, all these, that is the knowledge of language, knowledge of mathematics, and the knowledge of script, all these are co-joined with each other. So each field is seen to have grown best in the presence of the other. Now, they have separated from each other, and we are facing the dangers of over specialization in one area. So one who knows mathematics may not know the language Sanskrit, and vice versa. And if one knows Sanskrit and mathematics, he may not know how to read the manuscript because of the script. So these are the problems that we are facing now. So that I say it is a danger of over specialization in one area. So the combined effort of experts in all these separate areas is required. Now, search for any hidden new ideas, concepts, theories, formulae, etc. Focus on the methodology, motivations, rationale, the tools and techniques they have used in formulation of various results. Now get into the insights and inspirations of the ancient minds. Reconstruct the old methods, the old concepts, methodologies, and redefine them in modern terms. Fallacies, if any, are to be looked into. And sometimes even fallacies are capable of throwing light on the path towards the development of a discipline. Unwanted fallacies can be removed and update wherever it is necessary. Now, commentaries are rich source of methodology, motivations, proof, demonstrations, rationale, and updated knowledge. They are the best source to tap the springs of mathematical treasures. Now, another thing is the recovery of lost works. If it is completely lost, nothing can be done. But if citations are available, recovery of lost works to maximum possible extent can be done. Now, Mādhava's contributions are all obtained from citations only. Now, development of many commentaries are there containing citations from lost works, like Govindagudi, Jayadev's works, and so on. Now, we can develop teaching and learning tools. Instructive style of presentation is followed by many authors and commentators. The commentaries are potential source for looking into pedagogical aspects. They have given different types of proofs, especially in Kriyakamagari, we have different types of proofs for the same result. That is meant for different types of students. So they are given for students, the nature of the, depending on the nature of the students and the background of the students. Some student may be understanding easily using geometrical models. Another can be comfortable with the algebraic proof. Another student may be comfortable with only illustrations, examples, etc. So different types of proofs are given in Kriyakamagari, the commentary on Leelavadi by Shankaracharya. So such types of proofs or demonstrations are there. Several geometrical demonstrations of arithmetical and algebraic results are provided for visualizing and easy understanding of abstract concepts. Even series are treated geometrically. Arithmetic progressions, arithmetic series, geometric series are treated geometrically to visualize what is happening when taking the sum, nth term, and so on. Now, studies also for establishing the identities like summation results, Sankalita, Sankalita, etc. Varga Sankalita, Ghana Sankalita, etc. Sum of natural numbers, sum of squares, sum of natural numbers, sum of squares, sum of cubes, etc. are demonstrated geometrically, and several identities given by Chitrabhanu are established in a geometrical background. So one can easily understand abstract concepts by visualizing. Now, studies not only help to form teaching and learning tools for ancient concepts, but also they give idea to develop new ones for modern concepts and new ways of imparting knowledge to students with different nature coming from different backgrounds. With advancement of modern science and technology, and with the knowledge pouring from everywhere through our fingertips, it is the duty of the present generation to make the old flame of knowledge from the surviving mass of literature in the repositories into a splendid torch and make it glow as brightly as possible and hand it down to future generations along with own contributions. Thank you.